Welcome to Unit 5. At this point, we're going to continue our discussion on the solar system, looking specifically at the planets and dwarf planets within our solar system. So, just to begin, we need to understand what are planets and what are dwarf planets. I know there's a big debate out there. Pluto's a planet, Pluto's not a planet. We're going to clarify that in just a moment. We're also going to look at the planet that's closest to us, Earth. So we need to understand some of its systems, its planetary structure, and that'll give us insight into other planetary structures, especially terrestrial planets within our solar system. And then we're going to end tonight looking at those Jovian planets, looking at their features in terms of how they're composed and what are some unique items, unique features, if you will. So let's begin by defining a planet. A planet, according to the International Astronomical Union, as of 2006, a planet is going to be an object that meets three conditions. The first is it must be in orbit around the sun. So it must be some kind of object, it's orbiting around the sun. Cannot be a visiting object of any sort. 2, the planet has to have sufficient mass to assume hydrostatic equilibrium. What does that mean? Well, if we're getting to what we call hydrostatic equilibrium, basically we're saying that the planet has enough mass that due to its own gravitational pull, it is round. It is near round, it's near spherical, if you will. It cannot be some kind of jagged looking object that is going to just be pointing all over the place, or an oblong object. It does need to be round of some sort. So there goes all the asteroids, right? There goes all the comets. So we have objects that are in orbit around the sun, and we have objects that, due to their own gravitational pull, they are round. The third is going to be the object that is orbiting around the sun and round due to its own gravitation has to have cleared its local neighborhood. So what we're saying is, as this object is going around the sun, its orbital path must be near clear of pretty much any large objects. There can't be anything else within its orbital path that is a dominant object. Yes, it may have some smaller rocky materials flying through it. For example, we have a couple meteor fields which are very, very small, and we get meteor showers. But for the most part, our orbital path is completely clear. Now, here's the argument. A planet meets all three conditions. A dwarf planet, such as Pluto, Ceres, Haumea, Makemake, a couple different ones out there, a dwarf planet does not have a clear orbital path. So if you look at Ceres, for example, Ceres sits within the asteroid belt. Ceres definitely does not have a cleared orbital path when there are hundreds of thousands of objects floating around it. Very large as well. Pluto sits within the Kuiper belt, as well as Haumea, Makemake, etc. So those objects do not have cleared orbital paths. They are instead within the Kuiper belt, which is full of thousands of objects. And so they meet conditions 1 and 2, but in every case here, they do not meet condition number 3, which means that they are a minor planet or a dwarf planet. So when we're looking at dwarf planets in our solar system, Pluto's probably the most famous, but you've probably heard of Ceres in the news as of late. And there's also a couple other objects. So if you look towards the bottom left here, there's actually a diagram showing us Mercury, and it's scaled to show us the other dwarf planets within our solar system. Now Mercury is a planet, has a cleared orbital path that is round due to its own gravitation, and it does definitely orbit the sun. But the dwarf planets, if you look at those objects, they are much, much smaller than Mercury, which is the smallest terrestrial planet. And if you're looking at Pluto, it's not even the largest of the dwarf planets. Eris is actually much larger, just by a little bit. Now, if we're looking at the orbits of these dwarf planets, here's something that's really important to understand. Almost all of these dwarf planets orbit beyond Neptune's orbit. Pluto comes very close to Neptune's orbit, but almost all of the dwarf planets are beyond Neptune's orbit, by a great distance even. Ceres orbits within the asteroid belt. So Ceres is actually very close to us. Remember, that asteroid belt is only a couple astronomical units away from us. So we could easily send a mission to Ceres and then collect data, which we have done. So let's talk about Earth now. Understanding Earth is going to be critical to understanding the structure and composition of other planets, especially terrestrial planets within our solar system. So let's start off with the atmosphere. Our atmosphere is pretty unique, actually. Earth has an atmosphere that has several layers to it. And as you're increasing your altitude from the ground, you're actually going upwards into the atmosphere. Initially, your temperature will actually drop. So as you're traveling through the troposphere, your temperature, as you increase your altitude, drops. However, Earth actually increases its temperature within the atmosphere as you continue to go upwards. And then as you start moving out of the stratosphere, the temperature again drops. And then as you move out of the mesosphere, the temperature then again increases. Now, this is probably a very odd relationship. So why does it work the way it does? What we get to see is that a lot of our energy actually comes from the sun. So the sunlight that is coming to Earth passes through the atmosphere, and some of that sunlight is actually reflected out at the different layers before the sunlight even makes it to the surface. But the sunlight that does arrive on Earth's surface is going to bounce back out and basically reflect Earth light out into the space. But only a small portion of that light is actually going to be bounced out. So some of that light is actually trapped within our atmosphere, and it allows us to heat the surface, and then infrared radiation is going to leak a little bit into space, but it's going to be trapped within that troposphere region. That infrared radiation kind of works like a blanket. It keeps us nice and warm. A little too warm in Florida, but it does keep us nice and warm from the coldness of space. As you start moving upwards within your atmosphere, your temperature will drop because you're getting further from the surface, which is radiating that infrared radiation, which was heated from the sun. You're also now starting to see the temperature increase as you go to higher levels because it is getting more sunlight, and then some of that sunlight is being reflected out. So you're seeing this relationship of back and forth in terms of temperature based off of altitude. And that is, again, essentially working like a blanket, and it keeps our temperature here on Earth pretty mild, pretty stable. It allows us to have weather systems that are not going to be extremely harmful to the environment. Now, if we look at the atmosphere, what we get to see is that the atmosphere will actually cycle. So we notice that certain times of the year, certain regions on Earth have different features, especially weather pattern-wise. And we've all heard that if you go close to the equator, it's going to be very, very hot. Well, that's true, and here's why. The atmosphere is distributed into what we call convection cells. Convection cells are where you have hot and cold working together to create a cycle. So warm air will rise, cool air will drop. What we're seeing in the atmosphere is that this cycle, this convection cycle, works within a cell structure. So it stays within a region, generally speaking. And there are three major types of cells. You have the tropical cells, which are close to the equator, and then they go up to the Tropic of Capricorn, and the Tropic of Cancer. And those two regions are going to be labeled on any kind of map. So you have the equator, and then going north and south, you actually see the two tropics, Capricorn and Cancer. Those are boundaries for the next cell. And as you start looking in those next cells, you actually get what we call a temperate zone or a temperate cell. And that atmosphere is going to be a little bit more mild. It's not going to be as hot. It's not going to be as flourishing, if you will. And so as you start moving upwards or downwards in the temperate cells, you get to the polar regions. And those polar cells are going to be divided by the Arctic Circle and the Antarctic Circle. And those regions are very, very cold. So what we're seeing within the different temperate, polar, and tropical cells is different types of vegetation. So different types of life that can thrive in these environments. If you notice, if you've ever looked at a map, if you've noticed that the majority of deserts are close to the equator, the majority of deserts are within the tropical cells because they are very, very hot. Likewise, the majority of rainforests are also within that tropical cell because even though they're still very hot, they're also very humid because there's lots of water available to them. Now, your temperate cells, they're a little bit more stable, and then your polar cells have unique vegetation, unique life forms that can withstand the very cold temperatures. Now, if we're looking at the internal structure of Earth, as well as Earth's moon, what we notice is that the rock that's sitting in space, us, the moon, etc., is exposed on its outer layer to very cold temperatures. Now, Earth is blanketed, so it's not exposed directly to those cold temperatures, but it is still going to have some of the effects of what we call cooling, planetary cooling. Now, if we're looking at this structure, say the moon is just simply going to radiate its heat outwards. It's not keeping that heat within. As it ages, it's going to get colder, and eventually it will solidify. Earth, on the other hand, while it will still solidify, but it will take a much longer time frame, Earth actually has a different type of core structure. So it does radiate heat outwards, but it actually has convective cell motion under its surface, so under the crust, that is cycling hot and cold lava, magma, materials that are subsurface. We'll talk about that again in a moment. We also get to see, by evidence of earthquakes, two different core structures in the center of Earth. We have a liquid iron core and we have a solid iron core. The solid iron core sits at the very center, and then we see the liquid iron core moving around this solid iron core. Now, this is actually a very important process because when we're taking two iron cores like this, what we're actually getting is a lot of frictional motion, and that frictional motion is going to cause a lot of electromagnetic forces to actually occur. We get to see that the magnetic field of Earth is actually generated from within. We'll talk about the magnetosphere again in just a moment. Actually, we're going to talk about the magnetosphere right here. I forgot I moved it up. So the magnetosphere is actually going to be caused from, again, that core motion. And what we get to see more than anything else here is that we are being bombarded constantly by the sun. The sun is releasing quite literally billions of tons of material just every second. It's a lot of material. And we just happen to be in the path of the solar wind because we sit very close to the sun. Now, that solar wind, if we had no magnetosphere, would directly bombard Earth's atmosphere. It would start stripping it away because these are very fast-moving, very excited particles, and they will hit our slower-moving particles and just bump them off. However, because of our magnetosphere, the magnetosphere kind of works like a deflector shield. It actually diverts a lot of that solar wind around the planet. Now, some of this solar wind is going to actually pass down to Earth. Now, you may be thinking, okay, wait a minute, you just contradicted yourself. No, I didn't. Here's how it works. If you're looking at very high energy particles, very fast moving particles, they're very, very excited. and they are coming into contact with a magnetic field. They are very excited to see those magnetic fields. They are extremely happy to jump right onto them and follow the loops of the magnetic field. When we're looking at our magnetic field generated from our core, we get two polar regions, a magnetic north and a magnetic south. And that is not at a perfect axis of rotation. It's slightly off, and it will continue to move because it is a dynamic system. But what we get to see with our magnetic poles is that those are points that are weaker in our magnetic structure, in our magnetosphere, excuse me. So if solar radiation is if solar wind is pushing down with a little bit more than average solar particles, so a lot of material coming all at once at us, what will happen is some of those particles will actually come down and meet Earth's atmosphere. Very high levels of atmosphere, but still hit Earth's atmosphere. What we get to see are very beautiful displays of aurora borealis or aurora australis, which are northern or southern lights. Very beautiful displays. If you ever get the chance, please, please, please go check them out. So what we're seeing with those aurora is that, again, those particles are coming down from the sun. They're making it all the way down through the magnetosphere to the weakest points, and they're striking the atmosphere. So they're excited particles, and they will, just like the kitten lecture earlier on, where we talked about introducing energy into an atomic structure and then it re-emits that energy by leaping and falling atoms. The aurora are actually caused by this leaping and falling. So we get to see these particles striking our atoms within the atmosphere, and then they will leap and then fall again because they cannot sustain the energy level, and they re-emit light based off of the chemical elements that are actually present in what's being hit. So you see different colors within the overall aurora, and it's based off of what kind of chemicals are present. So lots of oxygen, lots of nitrogen, so you get greens and blues, and then you get to see some pinks. That's a little bit of hydrogen that's out there. So it depends on what kind of elements are actually being excited, and then they're leaping and falling to re-emit light. Now, we talked about Earth having its substructure where it has convection cells. And just to think about convection cells for a moment, in terms of a fluid, if you were to boil pasta, for example, what will happen is the pasta will start to move like this. Comes up, falls down, comes up, falls down, and it's getting hot, rises, and it cools and pushes down. Hot, cold, it's doing that kind of motion. The Earth works the same way, but it's a lot larger than a pan of pasta. So you're seeing this convective cell motion where hot materials close to the core are rising up to the crust, and then they're cooling as they're rising, and they're falling back down. Now, this kind of motion that is subsurface, subcretaceous if you will actually move continents. So you probably have heard of Pangaea at some point, the supercontinent. Pangaea was just the last supercontinent based off of the theory of plate tectonics. And there's actually very strong evidence showing us modern day tectonic motion. The evidence actually comes from seeing very similar types of fossils on different coastlines that are completely separated. So for example, South America and Africa, which in this image look very connected, part of Pangaea, when they would have separated, they would have had very similar life forms while they were still together. That separation meant that those life forms eventually passed away and they fossilized. We find very similar fossils on either coastline. The second piece of evidence, which is actually much more reliable in terms of its scientific basis, its measurement system, is the measurement using GPS. So if we measure continents in terms of their position with a GPS satellite, so top-down view, what we get to see is that we actually do have a little bit of a shift from year to year. Now, granted, it is a very minute amount of shift, but it is enough drift to suggest that plate tectonics is actually a plausible theory. So that plate tectonic motion would have come from convective cell motion, which is subcretaceous. The convection cell motion will move the plates so that it is either pushing the plates together, and when it pushes plates together, one of the plates will either converge so that it will push upwards and create very high mountain ranges, or it will basically fall down below. It will submerge so that you're actually getting one plate over another. And so you're doing this motion here. You also have motion where two plates are moving apart. And as the two plates are moving apart, something has to come to fill the space. So that magma, which is subcretaceous, as the plates are moving apart, will push up through the crack, and it will start forming new landmass. And what we get to see as evidence here is regions that are going to be, especially Pacific regions that are very active in volcanic activity, actually have a lot more of that separation of plates. We also get to see some of the collisions having some of that evidence of volcanic activity as well, in earthquakes and fault lines. So this subcretaceous process of convection is actually allowing us to see the continents drift, but we're seeing more than just continents drifting. We're seeing the formation of land and the destruction of land as it fits within the model of plate tectonics. Now, if we try to summarize just very briefly all of our terrestrial planets, what we get to see is that between Mercury, Venus, Earth, and Mars, the 4 terrestrial planets, there are some common features that we try to locate. The first is craters. Craters actually give us a very deep history of that particular celestial body and its weather systems that go with that celestial body, some of its subsurface, subcretaceous processes as well. We look for volcanic activity because that would suggest that the planet is no longer just in the process of cooling, or it is in the process of cooling. And so the volcanic activity will tell us how active, how alive this planet actually is. We also look for atmosphere. Now, Mercury has no atmosphere, but what we get to see is that Mercury is pretty much solidified. It sits very, very close to the sun. So even though Mercury is very hot on one side, it's very cold on the other, whichever face is not facing the sun directly at that moment. And so the atmosphere is actually very important because it allows us to determine weather patterns on that particular planet. We're going to talk about Venus and Mars in more depth in just a few moments. We'll talk about Mercury as well. The last thing we look for is evidence of plate tectonics. And this is still an area of deep research. We believe that Earth is the only terrestrial planet with plate tectonics as it's currently defined. However, there might be evidence that both Venus and Mars have different forms of plate tectonics, or may have had different forms of plate tectonics within their local history. So let's talk about Mercury first. We'll start closest and move further away. So if we're looking at Mercury, Mercury is pretty much a solidified ball. It's pretty much a rock, and it's very close to the sun. So when we're looking at Mercury, it has no atmosphere, and it has no evidence, because it is so small, it has no evidence of volcanic activity. Because of the lack of an atmosphere, it has no weather activity, which means that the craters that have occurred on Mercury throughout its history are pretty much perfectly preserved. So it's a great history record, if you will, for that particular planet. What we get to see as we look at Mercury's craters is we can see different time frames of where these craters would have actually occurred. So for example, if you see a very large crater and then you see smaller craters within it, that large crater was formed by something that struck Mercury, broke its surface, it smoothed out the bottom by pushing some of that liquid, that subcretaceous liquid up, which would have been magma, rocky materials, which cooled down, and then because it's liquid, it cooled as flat, relatively flat. And then the craters that are inside that larger crater occurred at a different time. And so we can determine, based off of the cratering, roughly the age of those craters, how quickly or how not so quickly, if you will, this particular planet cooled, when those craters may have occurred. If we look at the image here, you'll notice that with this large crater in the center, where the number 3 is pointing to, there's actually a distortion that runs through this crater. And that distortion is what we call a scarp. Now, the scarp is going to be caused from basically the planet cooling. So once the planet cools, it may not cool uniformly. And so part of it will cool a little bit quicker. The other part is still a little bit more liquid. It's a little warmer. And so what will happen is you actually crack. And so you're freezing down. Here's an easy way to kind of picture how scarps work, a little bit in reverse, if you will. If you take a piece of ice straight out of the freezer and you drop it into water, the first thing that's going to happen is it's going to see a temperature difference, moving out of a very cold, solidified, happy environment for the ice, all the way into water, which is much, much warmer. Even if it's cold water, it's still much warmer than the ice. And so what will happen is the ice will crack, and you can hear it. It's like that. So what's happening here is you're essentially forming scarps due to differences in temperature on the actual ice. Okay. Planets do the same thing, but much, much larger. Now, let's talk about craters. Craters are very, very unique, and we just talked about some on Mercury in terms of understanding how those craters will actually give us a history of that planetary object. So if we look at craters on other celestial objects, trying to get some history here, we can look at the moon, for example. The moon has no atmosphere. And when we look at the moon, we get to see different cratering evidence, very similar to that of Mercury. Now, we don't see any scarps as of yet on the moon, which suggests that it may possibly still be cooling. Okay, here's the second thing. If we start looking at craters on planets that have weather, so for example, Earth, that center image is actually a crater here on Earth. Notice that it does not look anything like a crater on the moon or even Mercury. The reason for this is because the weather has actually allowed geological activity to kind of smooth out this crater, allow vegetation to grow on it, distort the actual structure of the crater. You also have plate tectonic motion here on Earth, which may have actually even aided in how this crater was filled up. And as you can see in this image, it appears like we have some vegetation. We also have some liquid water that is within the structure of this crater. If we look at Mars, Mars present day does not have an abundance of liquid water on its surface. And so what we're seeing is craters that are very, very old, yes, but notice that these craters appear to be weathered. So whether that's due to geological activity, due to water flowing on the surface, possibly vegetation at one point in Mars history, who's to really say? We're still trying to research this area. But the craters are actually giving us a clue as to the history that was once on Mars, what may have existed there before. So let's talk about the geological activity. If you have a very large body, such as, let's say, the Earth, and a very small body, let's say Mercury, there's obviously a difference in size here. And so if we're looking at the comparison, the larger the body happens to be, the more slowly it will allow it to actually cool. So it has a lot more material that's very, very hot, that is subcretaceous. That material, even though it's going through its convection cells of hot, cold, eventually cools down and will continue to shrink inwards. Convection cells and radiative heat, if you will, coming out. But an object that's very, very small, Mercury, the moon, etc., those objects are going to cool much more quickly. And what we're seeing is that it's just radiating the heat out, especially if it has no atmosphere, because it's not containing any heat on the crust. Okay, now if we're looking at a cooled planet, again, remember Mercury, the cooling may not be uniform, and so it will form scarps. That's a geological activity that is indicating that essentially the planet is dead. It has cooled off. Okay. So if we're looking at the cratering evidence within our solar system based off of this geological activity, then what we get to see is that those smaller objects, which would have cooled much more quickly, cannot really erase their craters. So Mercury and the moon, for example, cannot erase their craters easily, because they are cooled down objects. Now, what that means is using the history of our solar system based off of our solar nebular hypothesis, which we talked about previously, when the sun releases a Tatari wind blowing away all the excess materials, the small proplids, some rocky objects, the excess gases, etc., it blows it out into the Oort cloud structure. But some of those objects don't make it as far as they need to stay in a very large orbit. Instead, they blow out, they're slowing down because they're colliding with other objects, etc. And due to the gravity of the sun, they actually fall back towards the sun, so the solar system in general, the local solar system, and they actually collide with planets that are here. So what we're seeing is this is going to be what we call the early and late heavy bombardment periods. This is where all the cratering really occurred within our solar system. So we have the early heavy bombardment, which is quite literally where the moon got most of its craters. And we get to see some other objects, such as Mercury, getting some of those craters as well. The late bombardment period, which happened a little bit later, if you will, but it was the last big time frame that we had where a lot of objects came in and struck the planets. The late bombardment period occurred later, and so those objects were able to cool down, so Mercury and the moon, for example. And then the late bombardment came in, created the craters within the craters. So that's where you're seeing the two different cratering histories. Over the last, give or take, 3.8 to 3.9 billion years, there's been very little overall bombardment. Now, that does not mean that we don't still get struck with objects, but it does mean that for the most part, all those excess materials that were blown out from the original solar system, while it was still a protoplanetary disk, those objects have either stabilized in their orbits or they've already collided with other objects. A few items here and there will come in and actually collide with any of the modern day planets. So let's move on to tectonics. If we look at Venus compared to Earth, what we get to see is Venus is very, very hot. Venus has a very thick atmosphere, which we'll talk about in a moment, but that essentially blankets all the heat into the actual planet on its surface. The surface of Venus is not visible directly because the atmosphere is so thick and it has haze layers. When we're looking at Venus, we actually have to get different spectra to gain a view of the surface of Venus. When we're looking at this particular image on the right, what we see is elevation of the different features on Venus. And for the most part, everything on Venus is relatively flat. There are a couple small areas where you have some peak regions going up into a few kilometers, but for the most part, everything is at what we would call sea level, or just below sea level. And so what we're seeing on Venus, because it is so flat and because it is so hot, is that it would actually have what we suspect to be super active convection cell motion underneath its surface. What we're seeing is these convection cells are, if you will, supercharged. They're very, very hot. They're just boiling. And your crust, as a result, cannot cool enough. So the crust on Venus is very thin, and it's allowing the crust to kind of crumble. So plate tectonic motion, like we see here on Earth, is definitely not present, because we would see much more vivid structure to the planet as opposed to flat lands. However, this super convective cell motion is also erasing all the cratering evidence that occurs on Venus very quickly. So if a crater were to occur, so if an object has struck Venus, then Venus is going to fill that space very quickly because the crust is very thin, so the liquid will come up. And then, as it cools, it's already being replaced. So that convective cell motion is erasing any kind of cratering evidence that we're going to see on Venus. Mars, on the other hand, is quite cool, actually. Mars, for the most part, has no evidence of plate tectonic motion at all. Whether Mars had plate tectonics at one point in its history or not, we don't know for certain. But what we do see are evidence of lots of regions that may be cooled off and then solidified. And if we look specifically at one region, it's called the Valles Marineris. As we look at this particular region, it is essentially like a giant scarp. It's a fault line, if you will. It's a tectonic crack. And so this crack is actually the length of the United States, give or take, and it's cracked so greatly that in some regions from top to bottom it is 5 miles in depth. So it is a very large crack, which means Mars was cooling and it did not cool evenly. So as it cooled, it did not cool evenly, it cracked, but the other regions on Mars are very featureless in terms of any kind of tectonic activity that might have occurred. Now, if we look at volcanic activity is very closely related to the tectonic activity, because what we're seeing with tectonic activity is that convection cell motion of fluids below the surface, and it is moving the plates, or moving, in Venus's case, the crumbly plates. In Mars, we don't see plates, but we do see a little bit of volcanic activity. So Venus is said to have highly active volcanic activity. It's constantly just pushing that material from subcretaceous to the crust level. It cools and then it crumbles. It keeps going. Earth, on the other hand, is a little bit active. We see pockets here and there, especially on the plate boundaries, where sometimes when there's a shift, material from subcretaceous regions will push upwards, and so we see lava coming from subcrust. So it's volcanic explosion. A lot of that volcanic activity, if you've ever wondered where you can go find some, is actually over in the Pacific region. There is actually an active volcano over in Hawaii that you can easily see how this volcanic material is actually being pushed up. That being said, a lot of volcanoes on Earth are also below the ocean floor, or below the ocean, on the ocean floor rather. If we look at Mars, there are a couple of regions where it appears that there might be some active volcanoes. This might suggest that Mars is still trying to cool. So we don't know for certain, but that is what we suspect. If we look at the atmospheric structure for each of these planets, remember Mercury has no atmosphere. Earth, we already talked about our atmosphere, and it has that blanket-like structure which keeps us nice and warm, but not too warm. Keeps us at a Goldilocks temperature, if you will. If we look at Venus, Venus has a very thick atmosphere, very, very high pressure as a result of this atmosphere being so thick. We also get to see many different layers of haze on Venus. So when we're trying to look down at Venus, we have haze blocking our view at every level, excuse me. So it's kind of like me putting up different screens so that you can't really see me very well. It's the same idea. It's like haze. So we have to use different types of light to be able to look down and see the surface of Venus. Here's the big difference. If you recall our quick reference about Kelvin, 300 Kelvin is about 80 degrees Fahrenheit, so a little above room temperature. Earth, on average, has about that 300 Kelvin, or about that 80 degree Fahrenheit temperature. Depends on what region you're in. Yes, it'll be a little bit different, but you can think of that as kind of average. Average on Venus is over 700 Kelvin. Over 700 Kelvin. That means the surface of Venus is going to be over 200 degrees Fahrenheit. It's very, very hot. It's like an oven, quite literally. You also have that crust, which is very crumbly, and that super active convective cell motion, so it's keeping the heat blanketed in. What we see as the haze layers on Venus is that this will actually trap heat. Now, as you increase your altitude on Venus, your temperature will drop substantially, and it will continue to drop substantially. Mars is actually very cold. So it's just the opposite. It's like fire and ice, and then Goldilocks in the middle. What we get to see on Mars is that the atmosphere is extremely thin. It is going to be really cold. So again, that 300 Kelvin is about 80 degrees Fahrenheit. We're seeing on Mars temperatures that may be about 260 degrees Kelvin. So it's very, very cold on average. Water will naturally freeze and then evaporate as well on Mars at the surface. Now, Mars does have a couple areas where it does have water ice clouds. The temperature will also decrease as you increase your altitude. And so it does have water ice, and it also has carbon dioxide ice, excuse me. You also have some dust clouds because Mars is a little bit of a dusty planet. It appears reddish because it is mostly oxidized materials. And so that is where it gets its name, the red planet. Now, if we look at Venus in terms of its atmosphere, Venus, again, is trapping all of that heat within its atmosphere at the surface level. You also have the surface, which is keeping it nice and warm with all that super convective cell motion and the volcanic activity. The pressure of Venus's atmosphere at the surface level would be enough that it could crush a car in under an hour, an average car. And so when we sent a probe out to Venus and crashed it onto the planet, it was able to actually collect some interesting data, send back a couple images before it was actually crushed and could no longer respond. The average temperature on the surface of Venus is about 864 degrees Fahrenheit, so it's very, very hot. Now, if we're trying to have water on Venus, H2O, it's too hot for water to actually exist in a liquid state on Venus. So it would be trapped in the atmosphere as a water vapor, and that water vapor is acting like a greenhouse gas to contain even more heat down at the surface level. If we look at Mars, again, just the opposite. It has what we call the runaway ice house effect. Mars can't keep enough heat in. And so Mars is very cold. What we get to see here is that, yes, there is a little bit of volcanic activity, but it's not a lot. Due to the thin atmosphere, Mars cannot heat up enough, so it will constantly cool, and it will cool a little bit faster. So water on Mars will actually exist in just a couple regions. It's mostly permafrost, which is subsurface. So you got to dig a little bit and you can find permafrost. You can also see the polar regions on Mars having lots of water. And we believe that we get to see a lot of not only H2O, but also frozen carbon dioxide mixed in with this water. Now, there has been more recent evidence suggesting that there might be seasons on Mars that allow a little bit of this permafrost to melt. And so it becomes a liquid state for a very short time frame, and then as soon as it becomes cold again, it freezes over. So why are we talking about water? Well, here on Earth, water is abundant, and it's in all the different states. It's gas, it's a liquid, and it's also an ice. But if we look at the other terrestrial planets, we want to know, what is water like on those planets? Well, let's start with Mercury. Mercury, being closest to the sun, is actually not going to contain an abundance of water. Go figure. It has no atmosphere. It's very close to the sun, very hot. In fact, you wouldn't think Mercury has any water whatsoever. But there are a couple regions in the polar regions of Mercury where they have permanently shadowed crater walls. And these permanently shadowed crater walls actually are never going to be exposed to sunlight. And so water ices will exist within those small pockets. So it's not in abundance, but it is water ice that is trapped on Mercury. We also have some regions on Mars where we get to see the ices, the water ices are trapped, again, in that permafrost state and towards the polar regions. It is not going to necessarily be a very abundant liquid state, even though there is a suggestion that there is a liquid state of water at different points in Mars seasons, if you will. Now, Venus is far too hot to actually have water at its surface. Venus will trap its water within the atmosphere, and that water will actually serve to trap even more heat down at the surface level. So it's like a constant vicious cycle, if you will, where the water is trapping the heat. So here's the big question. How do planets actually rotate? So we talked about some of the features of terrestrial planets, but how do these objects move? Well, they're solid objects. Granted, some of them have atmospheres, and they're not completely solid in general, but their rotation is similar to that of a solid object. So if we think about, say, an 8-ball, a cue ball, any kind of pool ball, any kind of solid object, as it rotates together, which means going from its polar region down to its equator, it will actually have different speeds so that the equatorial region will have to move faster to keep up with the rotation that we're experiencing at the pole. Okay. Now, here's the crazy thing. When we're looking at these gas giants, when we start talking about those in a moment, gas giants like Jupiter, Saturn, etc., do not have solid rotation because they are not solid. They are not even physically connected, except that they are gases. Gases are very fluid. And so when we're seeing this kind of rotation, gas giants, Jovian planets, will have what we call differential rotation. And the differential rotation will mean that the cloud structures, the atomic structures that are contained here, the gases, will move at different rates at different parts within even the same region. And as you're looking around the entire planet, they all have different speeds. Okay, so how do you relate to that? Well, think about water for a moment. If you have a cup of water, you have a pot of water, whatever, or coffee, if you put a spoon into it and you start stirring, towards the center, you're actually going to have very fast motion where that spoon is actually creating essentially a vortice. And then as you're looking outwards, you're seeing slower motion and you're seeing different motion. So if you were to drop some creamer in your coffee, for example, the fluid motion has to take effect to get that creamer nicely mixed in. But as you're mixing, notice that the creamer does not evenly distribute until after you've mixed quite a bit. That's because it has differential rotation. Okay, so how does this actually apply? Well, when we start getting into the gas giants, we have that differential rotation. We have to classify our gas giants pretty much in two different ways, based off of the chemical compositions in each of these planets, based off the features that we see. So we generally see lighter materials in these larger planets, and we have not been able to get any kind of probes deep into the planet to actually examine what's inside. Because of how much gases are there, the atmospheric pressure as you go deeper into the planet will grow so that it will crush any kind of device that we could send in. So what we get to see here is based off of our suspicion, based off of our observation, and based off of some of the unique features that we see from these planets. We classify our Jovian planets in two ways. We classify Jupiter and Saturn together because they are very similar in structure, and then we pair up Uranus and Neptune so that they are very similar in structure as well. And based off of observation, you can see here on the side, Jupiter and Saturn are very similar in color, very similar in size, and we can also see band structures which are very similar. If we look at Uranus and Neptune, they're both bluish, and so they have very similar features as well, also in size as well as color, which indicates chemical composition. So let's talk about Jupiter and Saturn. A lot of what we understood about Jupiter and Saturn, especially early on, came from the Voyager missions. And more recently, we were able to send more missions out to Jupiter and Saturn, such as Cassini and Juno. And the data that we're receiving from those missions is confirming and expanding on what we understood with Voyager. So if we're looking at Jupiter in terms of its planetary structure, Saturn as well, both are actually composed of mostly hydrogen and helium. And so there is no solid surface here. It is pretty much all gases, and it's even in some states liquid form. And so what we're seeing is that this structure is going to have very light elements throughout the entire planet. As we start getting closer to the core of either planet, what we see are some more exotic particles, things that are going to form a little bit more of a rocky core, something that is more metallic in structure. These exotic particles do not exist in that current state on the periodic table. But if we have something like metallic hydrogen, for example, metallic hydrogen is essentially an exotic hydrogen particle. It is very, very heavy, but it is still at the same time hydrogen. Now, what we're seeing as a key difference between both Jupiter and Saturn is how much either of these two planets actually has in terms of the different elements that make it up, so hydrogen and helium. Saturn, from what we understand, has more rocky core but less fluid, so less of the liquid helium and liquid metallic hydrogen. That would be a little bit sub-outer atmosphere. So that's what we're really seeing in terms of the internal structure. Now, we cannot send a probe inside either planet very far anyways and collect true data, because the pressures of the atmosphere on either planet would crush any kind of device that we would send in. Now, if we look at Jupiter specifically, we see some very unique features. Jupiter is like the gem of the sky, the gem of the solar system. What we get to see on Jupiter is, of course, the Great Red Spot. It's a wonderful item to look at, and it's a humongous weather system. Think of our hurricanes and then multiply that by magnitudes. It is just massive in size. It is rotating, and so as a weather system, over time it will eventually fade away. It will grow, it will fade. The Great Red Spot, since it's been identified, has been around for over 400 years, give or take. When we're looking at Jupiter, we also see band structures. And so if you look at Jupiter through a telescope, you see these brilliant whitish and brownish regions. And so if we look instead at visible light, but in infrared light, near and far infrared, what we get to see are that these structures will emit different levels of infrared radiation. And so here's the crazy thing. When we see Jupiter, we often think, oh, it's a beautiful, perfect sphere, gases and everything. It has that differential rotation. It's just staying together. But what we're actually seeing is a difference, instead of two-dimensional, a difference in altitude. So think of Jupiter in 3D for a moment. The whitish cloud structures that you're seeing are much higher altitude than the lower levels, the brownish regions. And so we're seeing a difference in altitude, but from such a great distance, it appears as if it's a two-dimensional shape. So what we're seeing is a lot of really unique features, and the core structure of Jupiter is going to be much warmer in general because you're getting deeper within the planet. The pressures are increasing, you have frictional movement of gases. The core of Jupiter is actually estimated to possibly be greater than the actual surface of the sun in terms of temperature. But with that same respect, as you start moving outwards from the core, you're cooling down, and you have this difference of temperature which will cause the weather systems to occur. So as we look at the cloud structures on both Jupiter and Saturn, we notice that we actually see very similar structure. So both have very similar chemical composition in terms of ammonia clouds, ammonia sulfide clouds, hydrogen mixed in with like oxygen, so we have water clouds. We have all types of really, really cool structure. And for the most part, both Jupiter and Saturn have near identical but different amounts of each kind of element in that structure. So we have the ammonia, and then we have ammonium hydrosulfide, and then we also have our water clouds. Now, again, as you're getting deeper within either of these planets, you're increasing your temperatures very quickly, actually. Again, we said that the surface of the sun is about 10,000 degrees Fahrenheit. We estimate that Jupiter's core temperature is possibly around 43,000 degrees Fahrenheit. So over 4 times that of the surface of the sun. But that is actually going to allow us to see the kind of weather systems that we actually expect on Jupiter. What we should actually see in terms of, say, the Great Red Spot. The differences in our overall cloud structure, showing us the high altitude and the low altitude, and that difference. So if we look at the structure of both Uranus and Neptune, notice that their core structures are very similar in terms of the rocky cores that sit at their center. They're very terrestrial planet-like, but they are not solidified, so they are going to be composed of heavier materials in general. These rocky structures are actually going to be much larger than the core structures on both Jupiter and Saturn. But if we look just outside of the core, notice that we're looking at a region that is kind of like an ammonia and water ocean. So it is a liquid region. It's highly compressed. Keep in mind these are very large planets still, and so the pressures on these planets are very, very intense. As we start going outwards from that liquid ocean of water and ammonia, we actually get a different kind of ocean, which is going to be liquid hydrogen and helium. So while these are gas giants, they're not necessarily gassy, but they are fluid, and so they still exhibit differential rotation. Now, as we're starting to see these planets, you got to keep in mind that they are very far from the sun. If we look at Neptune, for example, Neptune orbits at 30 astronomical units. It will receive about 1/900th of the amount of light that Earth actually receives from the sun. So it is a very cold region of space. If we look at Uranus in terms of its atmosphere, the Voyager missions really could not find anything on on Uranus. Uranus is going to be pretty much featureless in just visible light. So we have to start looking at really compiling all of our information from Uranus throughout the different spectra that we're observing and compile it to really do a lot of processing to understand what kind of band structure we see on Uranus. And what we discovered is that Uranus kind of sits on its side. We noticed that some of the cloud structures, especially the upper level cloud structures, are very, very cold, down into the -300s degree Fahrenheit. So those regions receiving very little sunlight are very, very cold, and the weather patterns on Uranus are almost non-existent. But we do see that differential rotation in terms of very super processed, computer processed band structures. Now, if we look at Neptune, Neptune actually had a very unique feature, which was what we called the Great Dark Spot. And this particular spot was very similar to, say, Jupiter's red spot, the giant red spot. And so when we're looking at that particular dark spot on Neptune, the evidence that we actually have that this is a weather system is we see it with the Voyager mission, and then as we get later data from Hubble, just a couple years difference, the Great Dark Spot is completely gone. So that's indicating that these weather systems are not permanent features, but they are instead due to possibly contraction within the planet. So as the planet is still continuing to cool at its core, it will release some of that excess heat outwards, and that excess heat mixes the cloud structure, or the ocean structure in this case, and it will create these very large weather systems. Neptune is also going to be very, very cold. Some of the higher level cloud structures that we see here, those little white clouds, those are actually going to be methane clouds. And so both Uranus and Neptune have a great deal of methane. That's why when the sunlight comes in to either planet, the light that is absorbed is the red and the green, but the light that is reflected is more bluish. And so what we get to see is more bluish color due to the methane in either planet. Now, if we talk about rings, the Jovian planets are actually very unique in the sense that they all have rings, but their rings are very, very different. So if we look at the rings on Saturn, for example, they're very vivid rings, probably one of the best features of Saturn. But if we tried to figure out whether or not we have rings on, say, Neptune or Uranus, or even Jupiter, we have to block the light from that particular planet to be able to identify that it has rings. But these rings are very thin, and they are very hard to find. So if we look at Saturn's rings to kind of understand what a ring is made out of, a planetary ring, what we notice with Saturn is that it has multiple ring structures. And each of these ring structures is composed of quite literally millions of little particles, sometimes even smaller chunks of ice and rock. And the chemical composition is identified by just looking at the reflective light, which is identifying it as those ices and rock pieces. But if you're looking at something very, very small, like the D ring is quite literally particle sized. So it is not something that is a chunk floating around. It is particle sized. It's dust sized pieces of ice and rock. From Earth, we can only identify the A, B, and C rings. But with a satellite flyby, we can identify the D ring, the E ring, and the G ring, as well as the F ring. So we can see a lot more rings on Saturn than what we previously thought. These rings are actually all separate because Saturn has a very unique feature. Saturn uses what we call shepherd moons, which keeps all of the ring materials in their relative orbit around Saturn. We believe that the rings were possibly created from moons that got a little too close to Saturn and then were gravitationally ripped apart. And so as their orbits got a little too close, they ripped into smaller and smaller pieces, eventually getting down to particle sizes for the D ring. The rings on Saturn are also visible only at certain times of the year in terms of their complete vividness. And it's based off of where Saturn is in our relative perspective with respect to the Sun. So if Saturn is going through its different seasons, if you will, sometimes the rings appear to disappear because they're blade on. Other times the rings are very vivid. Now the rings are always present, but our ability to see the rings will change based off of essentially this orbit. Again, if we're trying to detect the very dim rings on other planets such as Jupiter or Uranus, even Neptune, we have to block out the light from this particular planet with a telescope. We can also observe, as we transit the planet, a distant star that is in the background. As we transit, we collect light from that star, and if we see dips within the spectra, the luminosity within the spectra, we will see the different rings in terms of their structure. Now, as we're transiting, the planet will obviously block out some of the light, and so that time period will allow us to measure the size of the planet. And then going back through that transit process, the star becomes visible again, and we can see the rings one more time. This is allowing us to measure not only the size of the ring, but also the width of the ring, as well as its orbital placement around the planet. So, you survived planets. I know it was a very detailed lecture, but please make sure you review any of the supplemental materials that I provided, and also please make sure you check out this week's discussion forum and the assignment. If you have any questions whatsoever, please email me.